In this work, we present PARC, physics-based augmentation with reinforcement learning for character controllers. PARC is a framework that leverages machine learning and physics-based simulation to iteratively augment a motion dataset in order to extend the capabilities of motion controllers. PARC jointly trains a kinematic motion generator and a physics-based motion tracker in order to generate lifelike motions for traversing complex terrains. Humans excel in navigating diverse, complex environments with agile motor skills, exemplified by parkour practitioners performing dynamic maneuvers such as vaulting, climbing, and jumping. Developing simulated characters that can achieve comparable agility remains a significant challenge. Current state-of-the-art methods for training physics-based controllers predominantly rely on motion capture data, using imitation objectives to guide the learning process towards natural and human-like behaviors. The key limitation for these motion control tasks is data scarcity, especially for highly athletic behaviors, such as parkour and terrain traversal. PARC starts with a small initial motion terrain dataset consisting of core terrain traversal skills, such as climbing, jumping, and vaulting. This dataset is used to start an iterative physics-based augmentation process that progressively expands the capabilities of the controller. At each iteration, PARC trains a motion generator using the dataset from the previous iteration. The generator is then used to produce new data for traversing randomly generated terrains. Following this synthesis step, a tracking policy is trained via reinforcement learning to enable a physically simulated character to traverse diverse terrains by imitating both the existing motion dataset and the newly generated sequences. Once the tracking controller is trained, its motions are recorded as new physically corrected motion clips and then added to the dataset. This augmented dataset is then utilized to further refine the model in the next iteration. The procedure for generating new motions begins with defining a target terrain, which can be either randomly generated or manually designed. Next, an A-star path planner generates a plausible trajectory for moving from a starting point to an endpoint. Then, the motion generator is used auto-regressively to generate a kinematic motion sequence along the path. Finally, the tracking controller is used to enable a simulated character to follow the generated target motion, resulting in the final physically corrected motion. To test the effectiveness of PARC, we compare the motion generators from different iterations. As the dataset grows, the motion generator is able to generate more realistic motions that better conform to the surrounding terrain. Physics-based correction is vital for mitigating the addition of physically unrealistic motions to the dataset. Without the correction step, the PARC motion generator tends to produce physically implausible motions. Our data augmentation method discovered many interesting and novel behaviors, sequencing unique combinations of skills unseen in the original dataset. For example, climbing up the edge of a cliff after making a jump, and dropping down to catch onto the ledge of a lower platform. Once trained, the motion generator and motion tracking controller can be combined to enable a physically simulated character to traverse complex new terrains. The motion generator is first used to plan a target motion for moving through the environment, and the motion tracker is then used to control a simulated character to traverse through the terrain by following the target motion.